One of the month is uh next week, a week before midterm, uh, 15th of April. We will take a quiz. Okay, so there will be quiz one. Okay, and this is open book quiz, but no electronic devices are allowed. Only paper material you can get. Okay. So that's the quiz one. So it will cover all the materials we have done before this quiz. Ah, I mean, sorry. Yeah. So there will be quiz one in 15th of April, and this will be open book quiz. No electronic device allowed, but paper materials you can get. Okay. Okay. So this today lecture we will learn about the specific method that can achieve this object detection task. Okay. So as we already learned about, object detection, they are the task that detect these bounding boxes surrounding the object that we are wanting to seek. And then also we have to classify those bounding boxes based on their semantic classes. Okay. But this is slide we already discussed before. Okay, so the naive way to achieve this object detection would be applying multi-scale bounding boxes around these images in this kind of sliding window method. Okay, from top left to the bottom right, we apply these bounding boxes and crop the inside region and then classify those regions. Okay, but this is not a practical way. And also for object detection, the bounding box shapes have to also be variant. This should be also diverse to capture diverse object shape. So there should be even more bounding boxes. Okay, so if the width of the images are W and height is H, then the number of bounding box types also be multiplied. So, the number of bounding boxes are so many. So it will take a few hours maybe for us to achieve this object detection for an image. And this is impractical. But before the deep learning, actually, this type of method is prevail in machine learning or computer vision society. So this is the Viola-Jones facial detection algorithm that is also implemented in the OpenCV. Okay, in OpenCV, if you try to load some facial detection model, that would be the Viola-Jones facial detector, which is published in CVPR 2001. Okay, and they are indeed using this sliding window approach. Okay, but face is mostly square, contained in the square box. Okay, their scales are uh, could be varied, but their shapes are mostly square. So because of that, they could reduce the number of bounding boxes, but still there are many bounding boxes. Their algorithm works like this. They apply the sliding window, and for region within the sliding window, they extract some feature which is called as hierarchic feature. This is hand-engineered feature. The researchers revealed that these hierarchic features are best for the facial detection task at that time. So they are using this type of feature extraction algorithm and also uses the boosting algorithm to apply binary classification on the patches. Okay, so they are wanting to classify the patches into facial region or non-facial regions. Okay, but the thing is, this is the efficient algorithm. The highlight feature and boosting algorithms are efficient, but they are still work fine, but their accuracy is limited for the faces that pointing to the front. Okay, if someone sees someone's image seeing the side is not, trivially detected by this type of Viola-Jones algorithms. So their accuracy is limited. So always the computer vision researchers are wanting to improve the performance of the algorithm and wanting to apply the deep learning algorithm. But the thing is, if we apply CNNs in this way, it will take a lot of time and eventually it will be impractical. So the first thing the computer vision researchers are thinking was to reduce the number of bounding boxes. Okay, the first naive idea was reducing the number of bounding boxes. Okay, uh, if we can find image regions that are likely to contain the object, then that would be looks like this. Okay, not extracting all the bounding box from the top left to the bottom right. We can extract some. If we can do this, extracting some bounding boxes from the regions that are likely to contain objects, then the number of bounding boxes will be greatly reduced, and thereby the algorithm will become practical. Okay, so we call this type of algorithm as the selective search algorithm. And this selective search algorithm can extract 1,000 regions from the image instead of width multiplied by height multiplied by number, the types of bounding box, number of bounding box. They are extracting only 1,000 bounding boxes. Okay, so this would be million scale. Okay, but 1,000 is still improve a lot. Okay, by reducing great number of bounding boxes. Okay, but how to achieve this was the question. How we can find image regions that are likely to contain objects. Okay, so but the idea is considering their low level features of the images, color, texture, size, and shape similarity. I mean, the motivation for this selective search algorithm is if some inside the image, if some regions are having similar color, okay, if some regions are having similar color, then there could be object. Okay? So having similar color or texture features, anyways, if we extract some low level features and some regions there are similar features concentrated, then that region may have object. Okay, so this is the heuristic motivation for doing this selective search, applying this selective search algorithm. Okay. So, in OpenCV, you can, also implement this selective search algorithm easily. Okay, so this is the actual code for loading the selective search algorithm. Okay, I will skip this part. Okay, so from this type of images, they cluster the pixels features, color, texture, or other features, and if they are coherent, then they are tending to generate some bounding boxes. Okay, and then also they calculate some score for that regions and sort them by their score and get only 1,000 bounding boxes which has top scores. Okay, and we can get this type of bounding boxes. Okay, and the first successful object detector, the RCNN, which is the abbreviation for regional CNN. This is the first successful deep learning algorithm that achieved object detection task using the CNN method. Okay, so what they did was they first applied selective search algorithm and extract 1,000 to 2,000 bounding boxes, and then apply CNN on those regions. Okay, so this is the CNN, which is pre-trained using the ImageNet dataset, which is the largest scale image classification data. So we first pre-train these CNNs using the largest dataset we have, and then apply these CNN architectures to the extracted selective searched regions. And then, we can get some one-dimensional vector at the end because for these CNNs, we are removing the FC layers. So at the end of this ConvNet, we are getting some one-dimensional vector. Maybe their size would be this dimension, or depending on what we manipulate, the feature dimension could be different. Okay. Anyways, after that, we are applying the shallow learning machine learning algorithm, which is the SVM. Okay, and then classify those these fixed dimensional vectors. Okay, for describing the features of these regions. Okay, are you guys following this? Okay. This is the RCNN, which is the uh, early successful object detector, but still there are some limitations. Okay, so they are still slow. The first limitation is they are still slow. They are still have 1,000 bounding boxes. Okay, and we have to apply the CNNs 1,000 times. Okay, still that's very slow and not end-to-end trainable. That means if we can train some deep architecture, as I told you, uh, the first input, which is the image in our case, the final output Y, the label maybe in our case, we have to get this gradient to train every layers inside the deep architectures. Okay, to train to achieve this end-to-end trainability, we have to maybe get this gradient, which means the differentiation of the last variable respect to the first input. Okay, but these type of architectures we cannot do that. Okay, because maybe SVM we can make it differentiable, but anyways, in actual implementation, these two libraries will be different. Okay, but using careful design, careful implementation, we can make this differentiable. But the thing is, uh, this is the input image is the whole image, okay? But we are applying some selective search algorithm, which is not differentiable and get these patches first, okay? And the entire training is starting from these patches rather than from whole image. Are you guys following this? Okay. So this sentence is meaning that our architecture is not starting from the whole image, which is the initial input, but starting from the intermediate patches. Okay. So there's a room to improve our performance. Okay. And also, let's think about this. So if you are given let's say if you are given these patches, okay, and someone asks you to classify this patch according to the semantic classes, okay, then can you classify those patches? maybe not. Okay. So even humans have to have some context, okay, when classifying some patches. Okay, right? So classifying when given this as the features or images, classifying this solely is not optimal doing the patch classification. Okay, but even humans, when classifying these patches, if we can see the whole input images, then humans also can do better for this classification. Okay, are you guys understanding that? Okay, so starting from this input, small patches are similar to the first case. Okay, so ask humans to classify these small patches, okay, given only this information, okay? But if from the whole image, okay, if we can differentiate the final uh, semantic classes respect to the whole image, that is similar to using some of the whole image context when classifying the patches, okay? Are you guys understanding that? Okay. So, making this pipeline to be end-to-end trainable is maybe important. Okay. So, there are two problems. Okay. First, this is still very large number of bounding boxes used, so that is slow. And also, this is suboptimal because not end-to-end trainable. Okay. So there have been some, I mean, RCNN first proposed in the year of 2013. Okay, so after seeing the performance of AlexNet, which is published in URIPS 2012, the computer vision researchers are wanting to apply that in object detection task. Okay, in the year of 13, this is the simplest way of achieving the object detection. But 2 years later, this first RCNN algorithm appeared, which slightly improves the RCNN algorithm. By title, you can imagine that this algorithm would be faster than RCNN. Okay, and what they do is they how to say in CNN, you already know that there are the convolutional layers, okay, which processes the two-dimensional signals, okay, and then we apply the FC layer by flattening, okay, by flattening it into one-dimensional vector. Okay, you're already familiar with this, okay. And here, what we do is we only uses the former part. Okay, so I mean we only uses the pre-trained CNN networks and their former part and apply these convolutional layers to the whole image rather than the patches. We apply this to the whole images. Then their activation map, which is the feature map, we record this as the feature map, will be extracted like this. Okay, so this will be large in dimension and they are two-dimensional images. Okay, but you may feel like that because thinking when considering the characteristic of the convolutions, we are applying when doing the convolution we are applying this size corners across the images like this, okay? So, and by multiplying filter coefficients and image pixels and adding them, we can calculate the output maps one by one, okay? Are you guys understanding that, right? So what I want to say here is, when getting these two-dimensional features, the features for these image regions, this is the whole image input, and the features for these spatial regions will be retained in this feature regions. Okay, are you guys agree with this? Okay, because of the characteristic of the convolutions, which, how to say, uh, extract the output by multiplying nearby pixels, adding nearby pixels to generate this output. That is the characteristic of the convolutions. Because of that, the feature, the spatiality of features are retained. So that means the input image, these subregions features will be retained this spatial region. And for example, this region's feature will be retained in these regions. Are you guys agree with this? Okay. So because of that, after extracting this two-dimensional feature, instead of applying this how to say selective searched bounding boxes to the image domain, rather than doing this, we can extract the how to say we can crop the patches, the features, rather than cropping the actual images. Okay. So because the 2D features are retaining some spatial information, we don't have to crop these patches, but we can also crop these features, okay, using the selective search bounding boxes. Okay. That's the first thing you have to understand. Okay, so the high level idea is we will crop the feature levels, okay, and then for these features, we will apply the remaining differentiable layers to make the overall architectures. But the problem here is if we extract patches like this, then their dimensions will not be fixed. Okay, so for example, let's say uh, for these patches, it would be, for example, 200 by 200, right? Then there will be this number of feature pixels here, okay? And if this is some bounding box whose dimension is, for example, 200 by 50, then this will only have this number of element, okay? So are you guys understanding that? So their feature, if we extract the feature itself, how to say, their dimensions will not be retained. So to solve this problem, the fast RCNA authors are proposing this ROI pooling algorithm. Okay, so what they do is uh, pooling is the way of picking some values from the whole image. Okay, ROI is the region of interest. Okay, abbreviation for this. Okay, so what the algorithm works is, let's say this is the feature map. Okay, feature map. Okay, then and also if we apply this type of bounding boxes, then crop it, and you can think this as the cropped feature map. Okay, and if we want to apply 2 by 2 ROI pooling, then it looks like this. Okay, so uh, regardless of the original feature dimension, they are making this type of sub windows, but 2 by 2, having just 2 by 2 regions. Okay, so 1, 2, 3, 4. Okay, so in the width you have 2 sub regions, and in the height you have 2 sub regions. Okay, uh, I mean maybe you can apply this having these sub-regions to for the whole regions, okay? And also for the sub-regions, you can apply this type of 2 by 2 ROI pooling. Then anyways, in each sub-region, you will pick just one value, okay? You will pick just one value. Then the final result may have just 4 dimensions, okay? Because one values are picked from each sub-regions, okay, regardless of the original feature dimension. Okay, are you guys understanding that? Okay, so even though these extracted cropped features, their dimensions could be varied, you are applying ROI pooling after that, okay? And you can remain this feature dimension fixed, okay? After the ROI pooling, your feature dimension will be fixed, okay? Are you guys understanding this? Okay. And then you will apply fully connected layers by making those vector having the fixed dimensional vector, and then apply this FC layer after that, and eventually mapped to two output. The first output is the new bounding box information, and second is the class information. Okay, what they want to do is they are initially having this how to say boxes from the selective search, but the selective search algorithm is having the heuristics is not optimal. So given this, you are wanting to improve that, refine the initial bounding box, and so that I mean you will estimate on the width, height, the new anyways the new bounding box new bounding box their output. And the other hand, you will estimate the probability vector, and that is actually represented. The output is the probability vector for k classes, k semantic classes. This is the number of classes. So you are first estimating the probability for k classes, and this is the information for the bounding boxes. So when describing one bounding box, you need to describe their center positions, okay, and also the width and height. Okay, so when describing a bounding box, you need full information. So this is the two output, okay, and this is actually the loss function that is applied to probability. Okay, this is the cross entropy loss maybe, and this is the bounding box regression loss. Okay, and MSE loss will be mainly used for this bounding box regression. Okay, so actually that is applied here. Okay, and this is the cross entropy loss that is applying the ground truth semantic labels to this bounding box. And this is the location loss that is applied to this bounding box information. The naive L2, which is the MSC loss, could be applied here, but they are using the mixed L1 and L2 loss. Okay, so in practice, they think this is better than using just the MSC loss. Okay, but this is minor thing anyways. So you can just use MSC loss or the classification loss for the probability. Okay, so this is the fast RCNN algorithm. Are you guys understanding this? Okay, and when doing this, what you can achieve is you can now start from this whole input image, and then by applying this CNN, you can get some intermediate 2D feature, and then crop those 2D feature and apply FC layer and map it to the two output, which is the probability and locations. Okay, so now the entire pipeline is becoming to end-to-end trainable. Okay, it starts from the whole image, and by using differentiable convolutional layer, and also this operation is interpreted as differentiable because when cropping this, you can interpret that as multiplying 1 for this region and multiplying 0 for others. Okay, so it is composed of the multiplication operation. So this is also becoming the differentiable operation, and the later part using the FC, that is the differentiable part. and it is mapped to the probability of the semantic classes of that box and also the new bounding box information. So the last output is differentiable with respect to the initial input, which is the input images. Okay, are you guys understanding this? Okay, and because of that, as I told you, I mean, given only this patch, even humans are sometimes confused to properly classify this small patch. But now you can interpret these things as, I mean, when getting these two-dimensional features, it already, I mean, the CNN, their characteristics are like this. So it is convolved with nearby pixels to get the 1 pixel of the output. Okay, so this process is similar to accumulating nearby context information to that pixel's feature. So, I mean, these 2D pictures are already accumulating some whole images contextual features, okay? Because we are applying convolution operation to get this feature map from the whole image, okay? These features are somehow encoding the whole image context. And starting from here, we are applying FC to map it to probability and bounding box information. So it is similar to what humans do classify these patches. When classifying these patches, we are seeing nearby information, which is the context, okay? So faster RCNN, it is becoming robust in accuracy. And also because we are now applying ConvNet just one time to extract this feature map, and the remaining part, it is not using uh, multiple times, applied multiple times, okay? So, I mean, the entire time complexity is also becoming fast, okay? Previous in RCNN, we have to apply 2,000 times for these convnet operations, okay? But now we can just once apply and extracting the feature map and doing the remaining part. Okay, so because of that, the testing time is a lot faster, becoming faster, and also thanks to this characteristic, the performance is also becoming better than previous. Okay, and now the same year, the fast ICNN appeared, and by title, you can also imagine that this paper is faster than fast RCNN. Okay, so they also improved the fast RCNN in two aspects. The first one is in the speed. They are making them faster and making them more robust in accuracy as well. So what they did is they apply the convolutional layers one time for entire image and extract this feature map that is same as before. But previously, I mean, selective search algorithm that is separately executed, and I mean that was separately executed here. Selective search that they applied separately, and then used that information is used for this process. Okay, that is separate algorithm. But I mean selective search that is having some heuristics. Okay, so what they replaced in previous algorithm is they also estimate optimally infer the bounding boxes from the feature map. Okay, that is the advancement made here. So from this feature map, they are also extracting some selective search bounding boxes, and using that, they crop it and map to FC layers to map it to P and T, which is the probability and new bounding box information. Okay, are you guys understanding this? So because of that, they are removing some heuristics retained in the selective search process. They can further improve the performance as well as this because this selective search algorithm is iterative process which is slow in speed, but in this time we can make it one-time inference. Okay, so the speed is also becoming faster. Okay, so that is made advancement made in this faster RCNN. So they are solving some bottleneck contained in the region proposal of the fast RCNN algorithm and making it faster and robust. So this is the comparison of RCNN, fast RCNN, and this is the faster RCNN algorithm. And they extract multiple image regions using selective search and apply one CNN per region and classify each region. Okay, that is the RCNN, and that is consuming almost 1 minute. Okay, when inferring object detection information from an image, and this is the accuracy for this data. Okay, but fast RCNN, they are applying just one CNN on entire image and extract uh, features for each feature map. Okay, using the selective search bounding box, they are cropping the feature map and extract features and classify those features. Okay. Anyways, they are applying just one CNN one time, and greatly, you can see here, fast CNN, their time is greatly improved, and also the performance is slightly improved. Okay. And this is the faster CNN and removing the heuristics in the region proposal algorithm, and thereby they can achieve it faster, even more faster, within 1 second, and their accuracy is becoming better. Okay, this is the other data sets testing accuracy. So the faster RCNN, this has been prevailed object detection algorithm based on the CNN before the transformer. Okay, and the other important work for the object detection algorithm is YOLO. Okay, so YOLO, maybe that is the word frequently used by young peoples, and that's the abbreviation for you only live once. Okay, but here what they say is you only look once. Okay, and this is they are saying their algorithm is one stage algorithm. And they are pointing that these fast RCNN stream algorithms as the two-stage algorithms. Okay, why they are two-stage is first they detect some bounding boxes. That's the first stage, and second stage they classify those bounding boxes according to the semantic classes. Okay, in the sense, in that aspect, these algorithms are called as two-stage algorithm. But YOLO, they are saying their algorithm is one-stage algorithm. Okay. And what they do is they simultaneously estimate two output. So first, they divide the entire image into 7 by 7 grid. Okay. 7 is some hyperparameter, so you can control that actually. But in the original YOLO paper, they are using 7 as the hyperparameter. And then for each sub-regions, there are 49 sub-regions, but for each sub-region, you are estimating 2 bounding boxes and also 1 class information. Okay. So there will be 49 class information inferred, and there will be 98 bounding boxes inferred like this. Okay. And then we will filter out unnecessary bounding boxes and make the final prediction. That's the entire flow of this YOLO algorithm. And even though the algorithm, their pipeline is drawn like this, when seeing this, you can more properly understand what they are doing. Okay, so this is the input image. Okay, input image inputted to the entire YOLO algorithm, and this is actually the YOLO pipeline. And at the end, you may see their final output their dimension is 7 by 7 by 30. Okay. This 7 by 7 means we will infer 30-dimensional output vector for each subgrid. Okay, so as I already told you that there are 7 by 7 number of grid. Okay, so we will infer 30 dimension for this one subregions. Okay, that's why we will estimate 7 by 7 by 30 dimensional array as the output. Okay. I mean, you can adjust this 7 to others. Okay. You can use a 9 by 9 grid. Okay. By changing this dimension. And also this 30 dimension is 30 dimension because of this. So you will estimate two bounding boxes, as I told you. You will estimate two bounding boxes. And also, you are dealing with data sets having 20 number of classes. Okay. So, and one bounding box that is requiring 5-dimensional information. So you can use 3 bounding boxes instead of 2. Then you have to enlarge these vectors, okay, their dimension. By enlarge this vector dimension, you can adjust the number of bounding boxes estimated from one subregions, okay? And also, if you are dealing with other data sets having more than 20, then you can also adjust this dimension, okay? Okay, so this is the YOLO algorithm. So, and the inside this architecture, there are Google LUNet backbone and also many convolutions and will be nonlinear layers and fully connected layers. Okay, given the how to say ground truths made in this array type, you can train these differentiable layers to work for this object detection task. Okay, so in YOLO, the entire image comes to here, and the final output is outputting these two types. Okay, this two type information is inferred directly as this array form. Okay, so I mean, this information is contained in the 7 by 7 by 30 dimensional array. Okay, this 30-dimensional array having two bounding box information, and this is the 20 class probability information. So the output of the YOLO is having this, and they are indeed simultaneously estimate this bounding box information and also the class information. Okay, so that's why they are called as one stage algorithm. They directly estimate from the image, estimate these two information, okay, using the CNN architecture. And then apply, if you are given these two types of information, which is the 7 by 7 by 30 dimensional array, you will apply NMS algorithm, which is the non-maximal suppression algorithm. Okay, I mean, this is very trivial algorithm, and we also have some code for this in the later slide. What they do is they are suppressing non-maximal windows. So what they mean is here a lot of windows are intercepted, maybe intercepted, overlapped, many overlaps between there are many overlaps between the bounding boxes, okay? But given these bounding boxes, which is overlapped, we want to pick one bounding box, okay, which has highest score, okay? That is non-maximal suppression algorithm. I mean, among these bounding boxes, which has many overlap, okay, each other, we pick one bounding box that has the highest score. Okay, that is, in other words, that is suppressing non-maximal windows. Okay, so that's the non-NMS algorithm. When getting this 7 by 7 by 30 dimensional array, we are applying NMS to get this filtered output. Okay, That is the YOLO algorithm. And slide is showing why 5 dimensions have to be reserved for the window information. As I told you, when describing one bounding box, we need X coordinate, Y coordinate for the center position and their width and height. Okay. And the other fifth dimension is the confidence value, which is used for measuring the score for the bounding box. Okay. So using these scores, we will sort the bounding box and we'll apply the non-maximal suppression algorithm. Okay. So in YOLO, we are additionally estimating the score for the bounding box. Okay. So YOLO, each subregion, they are estimating 2 bounding box. You can also adjust the number of bounding box inferred from the subregion. And for 7x7 regions, you are estimating 98 boxes. Okay. And then apply NMS to filter out unnecessary bounding boxes, and that would be the final output. And this is the loss function for training this network. Okay. So in the later part, to properly estimate the 7x7x30 dimensional array, you have to apply some loss functions. Okay. And that will be like this. Okay. And that is very simple as well, even though this formula is very long. That is very simple. So for the X position, the center position of the bounding box, you will apply their ground truth center box. Okay. And this is the width and height. Okay. You are applying the L2 loss, which is the MSC loss for this. Okay. And for this part, this is applying loss functions for the confidence value, which is the fifth dimension value. Okay. And this is the probability vector. So here, I'm not sure why, but they are not applying the cross entropy loss, but instead apply this MSC loss even for the probability. Okay. And here, one thing you have to remember is this is some flag. Okay. So in each subregion, maybe 7x7 subregion, some regions contain the ground truth bounding boxes. Okay. And some regions, for example, here, they are not contain object. So this flag is meaning becoming one for example, these subregions that may contain ground truth bounding boxes. Okay. For example, here, for example, these subregions are their flag, object flag is one because there are bicycle bounding boxes like here. Okay. But for example, here, their object flag is 0 because they are background subregions and there is no ground truth they are containing. So this flag is becoming one for this foreground sub grid. Okay, they are applying this type of loss functions for the foreground subgrid, but this is becoming one for background subgrid, and they are only making this confidence value to be learned. Okay, and here the ground truth confidence value is set as 1 for the foreground region, but the background region they are becoming 0. Okay, so they are wanting to give highest confidence for the foreground bounding boxes estimated, and wanting to give the value close to 1, but wanting to give the value close to 0 for sorry. Value close to 0 for background regions. Okay, that's the thing happen here. Okay, And this is the non-maximal suppression visualizing their effect. So here there are a lot of bounding boxes overlapped each other, but among these overlapped bounding box, they are picking just one bounding box which has the highest score. Okay, that's the non-maximal suppression, and this is the implementation of NMS. Okay, so that's kind of involving some sorting algorithm and picking only the highest value when two bounding boxes are overlapped. Okay, they are picking just one bounding box having the higher score. That's implemented in here. Okay, and YOLO, this is published in the year of 2016. Okay, the important message here you have to remember is this is the speed axis and this is the accuracy axis. Okay, this is the precision and this is the frame, how many frames you can proceed per 1 second. So higher, you can process more algorithm, execute more algorithms per second. Okay, if your algorithm is fast, you can process more frames per second. So if you go this way, it is the faster, becoming means faster. And if you go this direction, it means more accurate algorithm. And here, what you have to remember here is RCNN that we have learned is located here, which is slow and having this amount of accuracy. But faster RCNN, that's becoming more faster compared to the RCNN. In the slightly right goes right, and their accuracy is becoming more robust. And faster RCNN their accuracy is becoming more accurate, and also their speed is becoming faster. So this is the relation between fast RCNN, fast RCNN, and fast RCNN. And you can see YOLO is located here. And normally we say certain algorithm is having more than 30 FPS, which means an algorithm can run more than, I mean, having more than 30 FPS, which means they can produce more than 30 frames applied more than 30 times per 1 second. Okay, so if some algorithm is located in the right side of this uh, 30 FPS, then we call that as the real-time algorithms. Okay, here that is not real-time algorithms. So these RCNN algorithms, they are two-stage algorithms, and by nature they are robust, but their speed is limited. Okay? YOLO, their accuracy is limited compared to the RCNN, but that is very fast algorithm. Okay. Okay. But I mean, YOLO version 2, they are improving the initial YOLO, and now YOLO is having version 12, as far as I know. Okay. So from this year of 2016, there have been a lot of improvement in the YOLO version 1. And there are many improvements in YOLO version 2. And in practice, this YOLO is real time and also having very good accuracy. So that is also used many times in the real environment. Okay, but still have some issues. Okay, but YOLO version 2, you can feel that depending on their backbone architecture, they are having some variant trade-off, but their accuracy is already improved compared to the faster ICNN. And also they are located in the right side of this graph, so they are real-time algorithm. So in YOLO version 2, they are already surpassing the faster ICNN. So many people, many company researchers or other researchers that wanting to apply this object detection algorithm in the real world applications, they are using this YOLO. Okay. But I mean, one critical, how to say, weaknesses in the YOLO algorithm is they are weak in recall aspect. So they always have to have two things to properly measure the performance of the object detection algorithm. The first is the accuracy, the precision. The other is recall. Okay, but I mean, in the previous slide, you can see this y-axis was only having the precision rather than the recall. 잘 안 보이나요? 이렇게 하면? Not sure why. 공유도 안 되네. Okay, anyways, I will continue maybe this part in next class. Okay. So anyways, the important message here is YOLO 아니 동작을 안 하지. YOLO it is I mean 저기에 있구나. 피아노. Okay. So I mean uh the x-axis is the speed. Speed and y-axis, that was the precision, which is one measure of measuring the accuracy, but that is only consist of precisions before. But important thing here we have to note is YOLO is having low recall, which is the weakness in YOLO algorithm. And I will explain in detail what is recall and what is the precision next time. And that is actually the last slide of this lecture slide. And why YOLO is weak in recall. And the later versions of the YOLO, they are trying to improve both recall and precision aspect. So I will briefly introduce that. And later we will learn about the transformer-based algorithms that do some segmentation, pose estimation, and object detection, and also image classification. Okay, so I mean, CNNs that is prevailed up until 2020, but after that, many algorithms are being replaced by the transformer, and also nowadays, Mamba algorithm is another alternative to the transformer. So we will learn about those kind of things in the remaining sessions. Okay. So for today, we will finish here. Thank you.